In this section, we will discuss a geometric interpretation of the cross product. Let's think we have a vector A and a vector B, and these two vectors form a parallelogram in a two-dimensional plane. So the area of this parallelogram is given by the height of this parallelogram and the base of the parallelogram. So it's simply the product of the base times the height. Here, the base is the length of the vector A and height, for example, is h, where h over the length of the hypotenuse is equal to the sine of the angle. So the height would be simply the magnitude of b times sine of theta. And this, by the previous theorem, can be written as the product, the cross product of the vectors. In fact, the magnitude cross product of the vector. Therefore, the length or magnitude of the cross product of two vectors A and B gives the area of the parallelogram formed by the vectors A and B as sides. Let's have a look at an example. We need to find the area of the parallelogram formed by the vectors A and B with components as shown. By the previous formula, we just need to calculate the length of the vector A cross B. We first need to calculate the cross product of A and B, which is a vector with components 14, 6, and 1. So its length can be given by the positive square root of the sum of the squares of the components, which is approximately 15.26 units. Now, if we calculate the cross product of the standard basis vectors I, j, k, we would obtain these formulas. I cross j is k, j cross k is I, and k cross I is j. This can easily be memorized by the following figure. If we cyclically permute I, j, and k, so this figure helps us remember the first three formulas. For example, I cross j, then we get k, then j cross k, we get I, and then k cross I, get j. Similarly, if we calculate the cross product of j with I, j cross I, we get negative k, and k cross j is negative I, and I cross k is negative j. This can be easily remembered by the same figure. If we move counterclockwise, for example, j cross I, we get k, K cross J, we get I, and I cross K, get J. Here, we observe that I cross J and J cross I are not the same vectors. Thus, the cross product is not commutative. We can also show that the cross product is not associative also. For example, if we calculate this, I cross J, we can show that this is not I cross J. That means we cannot move these parentheses. For example, the left-hand side is the vector I cross J. Since I cross J is K, and I cross K would be negative J. So the left-hand side is negative J. On the other hand side, we have I cross I, which is the zero vector, and the cross product of any vector with the zero vector is the zero vector. In general, the cross product is not associative. It is shown here. A cross B cross C, not same as A cross B cross C. However, some of the usual laws of algebra do hold for cross products.